Okay, let's go over another example here. We're going to use a cyclohexane ring again. And this is like a little side caveat to when you have a ring. And you really need to worry about this anticoplanar here with rings. But in particular, this one we can't always just look at the ring itself and see, okay, cool, we have these two protons and these two protons on our beta carbon. We have our alpha carbon here with our leaving group and our beta carbons. Okay, cool. Well, we have two protons that are opposite. These are both dashed. This should work. Here's the thing. So anytime you have this tert-butyl group, this is going to inhibit the ring flip. Or the chair flip that we're going to be doing in particular. I'm going to write chair flip. It's going to inhibit the chair flip, and this is really going to play a large role in this anticoplanar business. And I'm going to prove it to you here on this slide. So I'm going to move this down just a little bit. So we've got plenty of room. We're going to go through two examples. We're going to do this example, okay? And then on your second piece of paper, or give it some room later on, then we will do an example where we have that other diastereomer here. We have our trans substituted, 1,4 substituted cyclohexane ring. So first, let's go through the cis example. We're going to react it with KOH. And as you're looking, it looks clear that those protons are opposite of this leaving group, the ones with the pink dashes, but we need to prove it to ourselves. And the reason is the following. When we draw this chair, anytime you have a tert-butyl group, you're going to have inhibited ring flip. And I'm going to show you what that means. This tert-butyl group is up. So we're going to draw it equatorial up. Now, nominally, if we just think about this substituent, we could draw a ring flip. Okay. And this up position, it's still there, but it's now axial. So the only difference between these two is we went from equatorial to axial. Okay. Now, let's go ahead and draw in our leaving group. On the left side, we have it in the opposite side of the ring. It's on the 1, 2, 3. It's a 1,4 substituted ring. So it would be here. The bromine would be up in an axial. And actually, this is pretty good. In this case, we have protons here that are anticoplanar or antiperiplanar. And so this would actually work pretty well. Now let's go ahead and draw the ring flip and kind of get an understanding for this, because it's going to change what happens on the next slide. I'm going to put my bromine on this next slide, okay? If this is the 4 position, 2, 1. Our 1 position is here, and the bromine is going to be here, going up equatorial. Now, if you were asked which side of the ring flip is favored as far as which conformation is lower in energy, we're definitely going to say that this one on the left is lower in energy. So your equilibrium arrow would look like this. Now, I drew this with a very small amount going to this axial with this tert-butyl group. Remember that this group is huge. The energetic cost for it to go from equatorial to axial is around 4.5 or greater, actually, 4.5 kilocalories per mole. It takes a lot of energy for this large group to be sitting in this really uncomfortable axial position. And when we think about this, this could affect the reactivity of if an E2 could happen. Now, luckily in our example, when the tert-butyl is happy, okay, that means we have the highest concentration of this conformer because it's lower in energy, which means it is higher in concentration. There's an H there. So think about it this way. Just as much as we as humans like to be comfortable, organic molecules like to be comfortable too. Lower in energy is a good thing. Higher in concentration, most of the time this chair is going to be just as follows. Very little is going to be over here with this axial because it's so high in energy. So some professors will say that these terbutyl groups essentially lock the cyclohexane chair into this conformation. It's not quite true. There still is a very small amount of this, still technically in equilibrium. Very, very, very small percentage of this conformation. Okay, anyway, let's dive in. We know that our leaving group is in its happy place. It is anticoplanar to our hydrogen. This is a good thing. Now, there are 2 hydrogens here that are anticoplanar to that bromine. So I'm actually going to draw this second one. Let's do it with purple, and then we're going to see what happens between these two. So this one will be in purple, and the other one will be in red. So I'm going to label this one with a 1 in purple, and then I'm going to label this hydrogen with a 2. We're going to see what happens when we do an E2 with either one of these. Let's see what happens when we do the E2 with our 2 hydrogen. Okay, we've gone over the mechanism several times now, so I'm just going to draw the product from that. Here's my terbutyl group. If I number my carbons, so 1, 2, 3, 4, 5, 6. I'm looking at the 1, 2 position, getting the alkene. Okay. Now, if we make the E2 reaction happen on the this hydrogen 1. Now, remember, both hydrogens have an equal chance of undergoing an E2 reaction. And that's because there's nothing that's really different about them. Okay, they're both anticoplanar. None of them are favored by OH minus. It's just simply statistics here. So you get a 50-50 mixture of either one of those protons being plucked off by that OH minus. Now, if the purple one does, we're going to get this alkene. Do you see the difference between these 2 alkenes? Notice where the alkene is placed. Let's take this purple one and just confirm something. Let's go ahead and take it just like a pancake or grilled cheese on your stove. You're going to flip the whole molecule over. And when we flip it over, we still have our cyclohexane chair, but the double bond is now here. Okay, so I think of kind of like this, and then I'm just flipping everything over. So the double bond has moved, but we know that this wedge is coming forward, but if we flip it over, that means it's going back. This is not a mirror image, this is simply a flip. Pancake flip. All right, now, is there any relationship that's starting to come up? And I'm going to give you a little hint what's happening with these 2 guys. Remember, these 2 purple ones are in fact the same. So these are equivalent with those 3 arrows saying equivalent. So what's the relationship here with this green line between these 2? Well, the only difference is now we have a chiral center and it's either wedged or dashed. Yep. Bingo! I'm just assuming that you said that it was racemic. So if you didn't say racemic, that's fine too. Let me show you. It is racemic. I said bingo as if I heard you say racemic. Gosh, I'm nuts. Okay, racemic. On an exam, this is all you would write. You would just write one of them and write racemic. This is the product of this reaction. Okay, let's review what we just did. Number 1, we found out that there were 2 protons that are anticoplanar. I have them in red and purple. We did a chair flip just to discuss this idea of this anticoplanar being super important when we have a terbutyl group because it locks the terbutyl group. I say locks, there's still a small amount that can be present in the axial, just a super small amount. But this terbutyl group is like, yo, I'm going to be equatorial and I don't care what you say. And so the bromine, luckily on this compound, the bromine was wedged on this one position. So when you have a tert-butyl group, you do want to draw out your rings, okay? You want to draw out your chair, and you want to draw the equatorial, this tert-butyl in the equatorial position, and you're going to ask, can this leaving group undergo E2, okay? So we did all that, and we're going to go over an example where that can't happen, but we did all that, and then we looked at the product, and guess what? We practiced your favorite thing. We practiced using the word racemic. Okay, now the cool thing with this is that we actually start with just a cis compound. Okay, we didn't have racemic. We didn't have anything racemic in the first place. There was no chiral center. By doing the E2 reaction, we made a chiral center. And now, because there were two different protons we could take, that meant that we ended up getting a racemic mixture. Notice here that when you do the reaction, you won't know if you need to write racemic until you go through and see what product could form. Because we found out we had two protons that could undergo an E2 reaction, these two here. When you think about those two alkenes and draw them out, you realize they have a relationship that is enantiomers. So these two, this red and this purple, these are enantiomers. So in order to describe it, we would say the mixture of the product is racemic. Enantiomers is just saying, hey, we're brothers, sisters, cousins, whatever the relationship title is. Racemic is kind of like the family photo, okay? So they have a relationship together, and you would describe that relationship by taking a photo or writing racemic. Okay, let's now go over an example. This video is getting long as well. There you go. Cute cat break. Take a moment, roll your shoulders, stretch a little bit. Okay, about 10 more minutes left, I think. Okay, whew, let's do it. Let's now go over an example where this tert-butyl group causes some issues. We're going to go over the trans cyclohexane example here where the bromine is going down. We're going to react this with KOH. Let's draw our chair conformation. Now, I already told you there was going to be an issue, but let's just start out with the tert-butyl group in its happy place, okay? We all like to be in our happy place. All right, tert-butyl group, you win. Now, the bromine here is on the one position, but it's going down. Going down, here it is. Let's do a chair flip. Now, when we do the chair flip, the bromine is still going to be down, but now it's going to be axial. And the tert-butyl group still going to be up, but now it's axial as well. This is getting pretty unhappy. Okay, this is axial, this is axial. That tert-butyl group, so not okay with this. The equilibrium lies heavily on the left side. Just a little bit of this one. Now remember, this equilibrium is highlighting that this left side is lower in energy. And is favored. This conformation is favored. All right. So the problem with this is that we have a majority of this conformation and very little of this conformation. Now, we know that we need our proton to be anticoplanar to this leaving group. And unfortunately, with the leaving group here listed on this equatorial position, we cannot have that anticoplanar relationship. With the leaving group and the hydrogen. It can't happen. These two are, so this hydrogen's up This one's down, but notice that they aren't anticoplanar. That dihedral angle is not 180 degrees. Now, the problem is this is what the cyclohexane molecule here is sitting in. This is what it looks like. Very, very, very small percentage has the bromine and our desired beta protons we want to get rid of. It does have them in this anticoplanar relationship, but there's not a lot of it in our reaction. So I'm going to draw this here. An E2 reaction can happen. This is fast, just for this conformation, okay? And we will see a very small amount of our E2 reaction because this reaction is fast. But it's a very minor product. So even if a reaction is fast, you still have to have the starting material there. So only a small amount of this conformation is here, and so we don't get much of that E2 product. So now we have to go back to the drawing board a bit because you're like, yo, we're talking about E2. What the heck? Does it just not do a reaction? So in this case, we have to go back to our base. I know it's complicated, but this OH minus, it's a strong base, but it's actually pretty small. The itty bitty base, okay? OH minus can not only act as a base, but it can also act as a nucleophile. This is really where that SN2 versus E2 comes up again. We do have this secondary alpha carbon. It can undergo an SN2, although with strong bases, remember E2 is favored with strong bases. Well, in this case, we have a strong base, but it can't do the E2 because it has nothing to do the E2 on. There's only a very small amount it can even do an E2 on. So what happens is this OH minus is just hanging out with this secondary carbon with the leaving group, and eventually this reaction can go. Now, it'll do an SN2, but it's a slower reaction, okay? So instead of an E2, you're going to end up getting this slow SN2 reaction. I'm going to draw this over here. I'm going to draw an OH minus here in green. This poor OH minus keeps getting different colors. OH minus. I'm going to attack the carbon with the leaving group, and I'm going to kick out bromine. This is the SN2 mechanism. Remember, it's concerted. Okay, let's draw our product from this. You could draw it in the chair first if you'd like, or you can just draw it flat. We didn't touch this carbon. Now, this was a trans cyclohexane to start with. We did an SN2 on this carbon that I'm circling in pink or red, whatever color it is. That means that carbon is inverted, okay? The OH group is now on the other side. So let's do that. We have a wedge and an OH. So this OH group is coming towards us. This center is inverted. And this would actually be our major product. This would be a trans relationship, although simply drawing this molecule as an answer would give you full credit, okay? So what I'm highlighting here is that, again, if you have a ring, they can cause issues with anticoplanar, but in particular, if you have a tert-butyl group, that's when you're really going to want to start drawing out your cyclohexane chair. So the key thing is that you really only have to worry about this anticoplanar when you have the beta carbon or the alpha carbon with a chiral center. And we've talked about this. If they're both chiral centers, then you have to start worrying about it. And you have to worry about it if your beta and your alpha are in a ring. And if it's a cyclohexane chair, you can do this by just looking at it. So 4 6-membered rings. You need to consider this anticoplanar business when you have a tBu group. That's really the only group we're learning in this class that is going to inhibit, so it inhibits chair flip. Okay, for a lot of other 6-membered rings, I mean, you can just look at this one. And you can see here, this cyclohexane chair, this beta position has a hydrogen here. Totally cool. This chair can undergo ring flip. There's no tButyl group that's huge that's keeping it from that. So this can absolutely undergo E2 because our leaving group and our hydrogen are opposite on this ring. So there's plenty of ways to do these quickly. You don't have to work through them like this much each time. I gave you some examples where we really had to work through. And so that way you can see how it's done. But just know there's lots of ways you can kind of go stepwise. And if it starts to get more complicated where maybe you do have chiral centers or you do have a ring, sometimes with the ring you can just use this, but then just make sure and just check out those tButyl groups. And if you have a tButyl group, just make sure that your leaving group can be axial. And that means that then you can do an E2 reaction if you have a hydrogen on the beta carbon. Okay, and so I also wanted to show you, I re-recorded this video. Look at what I had done before that looks like a cluster. I'm not going to say the word, but I re-recorded it so it's a little nicer. Anyway, E2 reactions really go over all the concepts we've learned and just notice how our concepts are piling up. So make sure you stay on top of this. I hope these extra help videos helped you. If you like them, let me know and I will do my best to keep making them. I promise not to give you a mess like that on a video. I re-recorded this one like 3 times. Anyway, I hope that this extra video helped you and I'll see you in the next video. I don't know about you, but there's nothing like a cute cat right after some organic chemistry. Look, she's also studying with you. You're so good. You're so good.